Hello, guys, and welcome back to Math Zone African Motives. So, today I want us to start on our revision. I want us to start on our preparation for our March test. So, what I've done today is I've brought you a question paper which was written in March 2025. It was a controlled test from the district of OR Tambo, inland, which was from the province of Eastern Cape. So this was a question paper which came from the Department of Education from the province of Eastern Cape. So this is the question paper that I want us to use for our revision as we prepare for our March test. So you will see that this question paper was out of 75 marks and it was supposed to be written in 1 hour, 30 minutes. So let's get to see how much time we'll get to take in revising this question paper, as well as get to see and help each other on what is it that was expected of us and what is it that we are expected to know, how much depth we are supposed to go when we are revising as well as preparing for our upcoming March test. So you will see that this question paper has got a multiple choice section that is having 7 questions, and then it will be having structured questions. So you are always going to be given your multiple choice questions first, and then you'll be given structured questions. So question number 1 is your multiple choice questions, and they are saying that various options are provided as possible answers to the following questions, and each question would be having only one correct answer. So from the possible various answers that are given, you're supposed to only choose one correct answer. Out of A, B, C, and D, there is always only one correct answer. So let's see what question number 1.1 was saying. What is the term used for the distance between two successive points in phase? What is the term that is used to name or else to describe the distance between two successive points in phase? That is what we refer to as what? As a wavelength. You would remember that, let's say that you have got a wave, which would be a transverse wave. You would have to see that this point A is in phase with this point B. So these two successive points in phase will give you something that we refer to as your what? As your wavelength. So that becomes the distance in between two successive points. That is your wavelength. So that was the answer that they were looking for, which is B. Now you would see that amplitude is the distance that your particle is going to be displaced. So this is the maximum distance in which your particle would be what? Would be displaced. So that becomes your amplitude. Because some will start asking that why is it not the amplitude? The amplitude is the maximum distance in which your particle would be displaced. 1.2 is now saying the speed of a pulse is determined by the what? What determines the speed of the pulse? Is it the pulse length of the phase? Is it the pulse length of the pulse? Is it the amplitude of the pulse? Is it the medium through which the pulse travels? Is it the distance the pulse travels? So you see that the medium in which the pulse travels, the medium through which the pulse travels will determine the speed of your pulse. If it is more dense, then it simply means that the speed would be what? Would be low. It is less dense, then your speed would be high. So we are saying that the medium through which the pulse travels determines the speed of your what? Of your pulse. Now let's get to see 1.3. 1.3 is now saying which of the following diagrams best illustrates pulses which will interfere constructively when they meet up with each other. So they're just saying choose from A, B, C, D, which diagram represents constructive interference. We know that whenever we have got constructive interference, we are going to have a large amplitude. So constructive interference results into a what? Into a large amplitude. And also, constructive interference occurs whenever we've got two pulses which are moving in two opposite directions, mean to say that two pulses have to be moving in different directions, and they both either have two troughs or else they are having what? Two crests. So that is what we are looking for here. So you will see that you have got option A and you have got option B. That is where you have got either two troughs or else you are either having what? Two crests. But you will see that on this one, these two waves are going in the same direction, or these two pulses are moving in the same direction. Therefore, these two pulses are in phase and they will never meet because they are in phase and moving in the same direction. So our answer was going to be A. That was going to be our answer. Our answer was going to be A. That is where you are going to have constructive interference. Now let's look at 1.4. 1.4 is saying when the frequency of vibration of a wave with a period t is doubled, then its period is what? We know that frequency can be given by 1 over t, where if you interchange these two, your period will also be given as 1 over the frequency. So the period t is 1 over f. Now, what is the new period when we have got our frequency being doubled? Our frequency, they are saying when the frequency of the vibration of a wave with the period t is doubled. So what is doubled is the frequency. And then now they say its period becomes what? So its period will simply become 1 over 2 times t. So you would see that it becomes what? 0.5 of its period. I'm sure you can understand this, guys. We are saying that our period is given by 1 over frequency. Now I'm now saying that our new period is now equal to 1 over 2 of f, because this is the one that is doubled. So it's more like I would factor out 1 over half, and then I would remain with 1 over f here, which is just my period t, and 1/2 is 0.5, and that becomes 0.5 t. So our answer was going to be C. So guys, I would advise you strongly that whenever you are attempting your multiple choice questions, try by all means to use all the laws that you know to reason through so that you can be able to choose the most accurate answer. Don't do guesswork. Now let's look on our question 1.5. Which electromagnetic wave has the highest energy between X-rays, infrared, ultraviolet, and gamma rays? We know that we would start with what? With infrared. We usually start with radio waves. Radio waves. This is your electromagnetic spectrum, radio waves, and then we get to go to what? To infrared. After infrared, we go to visible light. After visible light, ultraviolet. After ultraviolet, you have got your X-rays. After your X-rays, you have got your gamma rays. So what is happening here is that you would see that we are having an increase in your frequency as we are going that side. So these ones will have a what? A higher frequency. As they are having a higher frequency, we know that our energy would be given by HF, where this H is our Planck's constant. So anything that is having a higher frequency will also have a higher energy. So here they're saying which electromagnetic wave has the highest energy. That becomes our gamma rays, because our gamma rays has got the what? The highest frequency. Therefore, it will be having a higher energy. That's why gamma rays are said to be the most dangerous waves, or the most dangerous electromagnetic waves. Why? Because they have got the highest penetrating power due to their highest energy. So our answer was going to be D. Now 1.6 is saying three charges X, Y, and Z are arranged in a straight line. X is positively charged and it is repelled by Y. So here they are saying that I have got X and X is positively charged. And they are saying that X is being repelled by what? By Y. We know that like poles they repel and unlike poles attract. So Y should be what? Should be positive. And then they are now saying, and Z is attracted by Y. So we are having Z, and Z is being attracted by Y. So if Z is being attracted by Y, to get to say that we are seeing our Z being attracted by Y, it simply means that this is negative. Now they are saying, what is the nature of charges Y and Z? Y should be a positive because it is being repelled by X, because X is a positive charge. So Y is positive. And then Z should be negative because it is being attracted by Y. We said like poles, they attract. These ones, they attract. Whilst unlike poles, they repel. So this one should be a negative. So our answer there becomes D because this is where we have got two ticks. So our answer there was supposed to be what? To be D. Now let's look at question number 1.7, which marks the last question on our what? On our multiple choice questions. The SI unit for volt is the same as what? So you would see that volt represents, or else it measures the what? The voltage, or else it measures the potential difference. It measured the potential difference. This is a measure of the potential difference across your what? Across your conductor. And we know that potential difference across your conductor is given by the work done per unit electric charge. Work done per unit electric charge. And we know that our work done is measured in what? Our work done is measured in joules, and our unit charge is measured in coulombs. So this is simple as joules per coulomb. So our answer here was supposed to be D as well. So you can see that I used the definition of what? Or the definition of potential difference to get the SI units, which is equivalent to what? To volt. I did not just guess it. So guys, let's desist from the way, or else let's move away from that culture of guessing when it comes to multiple choice questions, and let's try to use all of our physics laws, or else our physical science laws, to choose the correct answer. Now let's look at question number 2. Now we have started our structured questions. Question number 2, it is saying two pulses P and Q, they travel along a string and approach each other at the same speed. Both pulses have pulse length 8 centimeters. Pulse P has an amplitude of 6 centimeters, and this is pulse P. They have got the same length, 8 centimeters. But when it comes to their amplitude, pulse P is having an amplitude of positive 6 centimeters when it is at position X. Pulse Q is an amplitude of negative 8 centimeters when it is at position Y. Points X and Y are the same distance from point Z. So from point Z to point Q is the same distance as from point Z to point X. Pulse P and Q, they meet at point Z, mean to say they are going to have some interference when they reach point Z. Assume that no energy is lost. So assume what? That energy is conserved. Now they are saying define the principle of superposition. The principle of superposition tells us that when two pulses meet, the total sum of their amplitude is given by the sum of their individual what? Amplitude. That is what the principle of superposition tells us. So the principle of superposition just tells us that the resulting amplitude after interference is equal to the sum of individual amplitudes of the two pulses. So whenever we have got an interference, the resulting amplitude after that interference, like for example here, we have got a pulse that is moving in that direction, which has got this amplitude. Let me call this A1. I would call that what? A1. So we have got amplitude A1. And then we have got this pulse which is also moving in that direction, and it has got a pulse amplitude of what? Of A2. So we are saying that the resulting amplitude, which is the resultant amplitude there, would be the sum of A1 plus A2. So it becomes the vector sum of the two amplitudes. So vector sum, it means that you are also looking at the direction. Is it a positive? Is it a negative? Now let's hear what 2.1 is saying. What kind of interference will happen when these two pulses P and Q meet at point Z? We are going to have a destructive interference, like the one that I have been showing here. We are going to have a destructive what? Interference here. Why are we going to have a destructive interference? Because now the resultant amplitude, let me say that the resultant amplitude, let me calculate that, it is going to be positive 6 plus negative 8. That gives you a negative 2 centimeters. So you can see that the resulting amplitude is smaller. So we are going to result in a smaller amplitude. So this amplitude is smaller than the 6 centimeters, which is also smaller than this 8 centimeters. So that becomes the destructive interference. So we are going to have what we refer to as the what? Destructive interference. So you are going to choose destructive interference. And then they are saying, explain your answer, because the resulting amplitude has a smaller magnitude. What it simply means is that the size of the resulting amplitude is smaller. So whenever we've got a destructive interference, we are going to result in a smaller amplitude. But whenever we've got a constructive interference like this, we have got two pulses. This pulse is going that side and that pulse is going that side. What is going to happen is I'm going to have, let's say this is my first pulse, and then I'm also going to have my second pulse starting on top of this, so that the resulting amplitude becomes the sum of the two. So that if this was 2 centimeters and this was 2 centimeters, I would have a resulting amplitude of 4 centimeters. So you can see that the magnitude of the resulting amplitude is big, or else is large. So we are going to result in a larger amplitude. So that becomes the constructive interference. But whenever we've got a destructive interference, we are going to result in a smaller amplitude. Calculate the amplitude of the resulting pulse. So the amplitude of the resulting pulse becomes equal to positive 6 plus negative 6, negative 8, sorry. So this is the positive 6 of this amplitude 1, and then the negative 8 of that amplitude 2. You just add those two. So it becomes what? Negative 2 centimeters. If you add positive 6 and negative 6 gives you negative 2 centimeters. So that is what you were supposed to do for question number 2. Question number 3 is now saying the diagram below represents a transverse wave with a frequency of 1.5 Hertz moving to the right. So this is the wave that is moving to the right, and they are telling us that it is a transverse wave. Now they are saying define the term transverse wave. A transverse wave is a wave um, is a wave propagation. It's a wave propagation where the wave particles are displaced perpendicular to the direction of propagation of the wave. What it simply means is the wave particles, you can see that as they are moving, they are displaced up and down. I'm sure you can see that as the wave particles are moving, they are displaced up and what? And down. They move up and they also come down. So their displacement is this direction, which is up or else down. But the direction of the movement of the wave is towards the right. So you can see that these two are at right angles. So that is what we call perpendicular to each other. So the direction of displacement of the wave particles is perpendicular to the direction of the propagation of the wave, or the direction of the movement of the wave. That is what you simply write there. Or you can simply say that the direction in which the particles of the waves is in right angles with the direction of the what? Of the propagation of the wave. Write down the names of the following 2 points that are in phase. 2 points that are in phase, we can say that we have got point A and point C. Those 2 points are in phase. So I can say that point A and point C are in phase. Point A and point C, they are in phase. So you would say point A and point C are in phase. And then, what is the name of point B? Point B represents a trough. We know that the lowest point of a wave is called a trough, and the highest point of a wave is called a crest. Now they are saying point D. Point D also represents a what? A crest. So we have got a crest here, we've got a crest there, we've got a crest there. We've got a trough here, a trough here, and a trough here. So the lowest point of a wave is called a trough. The highest point of a wave is called a crest. So that is what you are just supposed to write there on your answers. So you were just going to come here and write that the lowest point of a wave is a trough. And then the highest point of a wave is a crest. Now they are now saying, let me just bring it like this. Determine the following in meters. Determine the wavelength. Determine the wavelength. Allow me to just get to rub here. We now want to determine our wavelength given the information that is on that diagram. So you would see that our wavelength is simply a measurement of the distance between two successive points in phase. Two successive points in phase, it simply means that one point after the other which are in phase, that becomes our wavelength. Now, I've got 2 points that are in phase, which is point A and point C, but they are not successive points, which means that I also have got another point that is in phase with A, which is to say if I move like this and then I come back, one complete cycle, I would have that point in phase. Another complete cycle, I will have that. So I've got two wavelengths here. I've got the first wavelength there, and then I've got the second wavelength there. So these two wavelengths, so you would see that two wavelengths are equal to the distance which is in equal to 4 meters. So one wavelength would be equal to what? I just divide by 2 there. I just divide by 2. So that 2 into 2 is 1. 1 times lambda becomes lambda. So that my 1 wavelength. One wavelength would be equal to what? 24. It becomes 2 meters. That is simply how I would measure my wavelength there. So my wavelength here was supposed to be equal to 2 meters. Now they are saying calculate the period of the wave. We know that the period of the wave, which is t, is given by what? 1 over the frequency. Now, are we given any information to do with the frequency? They said the diagram below represents the transverse wave with a frequency of what? With a frequency of 1.5 hertz. So now I know my frequency. So I can calculate my what? My period. That is just 1 over 1.5 hertz. And this is going to give you time in second, because hertz just simply means 1 per unit second. So if I have 1 per unit second, it will end up giving me seconds. So it's 1 over 1.5. So what is 1 divided by 1.5? Let's use our calculators. We are going to get an answer that says what? 3 over 2, or else 0.66. So this would be 0.667 seconds. So my answer here is just supposed to be 0.667 seconds, or else my answer would be 3 over 2 seconds, like that. Now they're saying calculate the speed of the wave. Calculate the speed of the wave. So how do I calculate the speed of the wave? I have got what we refer to as the wave equation. The wave equation says V is equals to F lambda, meaning to say that the speed of the wave is given by the frequency times the what? The wavelength, times the wavelength. So now I'll substitute what I have so that I can find what I do not have. So I'm looking for the speed. I've got my frequency, which is what? I saw that my frequency is 1.5. And I've got my wavelength. And then we said our wavelength is what? 2 meters. So I would say 2 times 1.5. That will give me an answer of what? Of 3 meters per second. Because I said this is the same as 1.5 1 over second, like that, because hertz means 1 over second, and this is in meters. So my units there would be meters per second, or else it would be 3 meters per unit second. That is the measure of speed. So that would become 3 meters per second. That is my speed. Let's get to see question number 4. So you will see that question number 4 is now saying, define the term longitudinal wave, and you are given a diagram above. So you can see that from the diagram above, I have got the propagation of a longitudinal wave. So what is a longitudinal wave? A longitudinal wave is a wave, or else is a wave propagation. This is a wave propagation. Or I can simply that a longitudinal wave is a wave whose particles are displaced parallel to the direction of the wave. So a longitudinal wave is when particles, or else you can say is when particles, when you do not want to repeat the word wave, is when particles of the wave are displaced parallel to the direction of the movement of the wave. You choose in which definition you would want to use, but we are just simply saying that you would see that here the particles of the waves are displaced towards that direction, whilst the wave is also moving in that direction. So these two are in parallel, because that is the reason why you now start to see some rarefactions and some compressions. So the particles are compressed and then they are stretched. They are compressed and they are stretched. So the movement is what? Back and forth. So the movement is back and forth. It's either we move forward or else we move backward in terms of the displacement. That becomes what we refer to as the displacement of the particles of the waves. So that is what a longitudinal wave simply means there. So you can choose which definition you want to choose. Now they are saying write down the name of labels A, B, and C. What is A? A represents a rarefaction. And what is B? B represents a what? A compression. And what is C? You can see that C is representing a distance from a rarefaction to a rarefaction. So a rarefaction is in phase with a rarefaction. So these are two consecutive points in phase. That gives you a what? That gives you a wavelength. So this represents a wavelength. We know that a rarefaction is in phase with a rarefaction. And whenever we have got 2 points which are in phase and those 2 points are successive, whenever we have got 2 successive points, these are successive points in phase, that becomes the what? The wavelength. That becomes the wavelength of a wave. So that was what you were supposed to write there. Those were the answers for question number 4 up to here. So you will see that question number 4 continues to question number 4.3 and 4.4 to make a total of what? 10 marks. So question number 4.3, we are given an explanation on top there, or else we are given a paragraph which is saying, the diagram below shows a boat which emits ultrasound to detect the depth of the sea. So we are emitting some ultrasound there. Those are the ultrasounds that are being emitted from this boat so as to detect the depth. So this would become the depth, which is the height of the sea. That is what we refer to as the depth. So we use ultrasound to actually get to determine that depth. So now they're saying the boat emitted a sound of frequency 30,000 hertz and return a signal or else a return signal received in the boat is received 10 seconds later. So this is the time it took to send signal there and also gets to receive them back. Now they're saying take the speed of the sound waves in water to be 1,500 meters per second. So for us to measure this depth, what we do is we send some ultrasound from the boat. And that ultrasound, we measure the time it will take to come back. So we measure the time taken to come back. Once we have determined that time taken to come back, because we know that V is equals to F lambda, by knowing the frequency of the sound that we would have sent, that becomes 30,000 hertz. And by knowing the wavelength of that sound, we can be able to determine its speed. By knowing the speed, we know that speed is equal to what? Distance traveled per unit time. By knowing that distance, we know that the distance that will be traveled, it will be 2 times the depth of the what? Of this sea. We can be able to calculate that depth. That is simply how we use ultrasound to determine the depth of the what? Of the sea level. So now let's look at the questions that are given. Calculate the wavelength of the ultrasound in water. I've already said that V is equal to F lambda. That becomes the equation of the what? Of the wave. Now, am I given this V? Yes, I'm given the speed of the sound. That becomes 1,500. equal to, am I given this frequency? Yes, I'm given that frequency. That becomes 30,000. So what is left now is my wavelength. So here I would come and say my wavelength is equal to what? 1,500 divided by 30,000. I will just get to divide throughout by 30,000. These will cancel out and then I'll be left with that. So I'll be left with what? Lambda being equal to 1,500 divided by 30,000. I'll just go to my calculator. I punch 1,500 divided by 30,000. That gives me a wavelength of what? That gives me a wavelength of 0.05 meters. And my wavelength is distance in between two successive points. That becomes a measurement in meters. So my wavelength there would be equal to 0.05 meters. So this is how you were supposed to calculate it. So let me just repeat what I've just said so that someone can actually get to follow how we're supposed to calculate this wavelength. So I would come here and say that V is equals to F times lambda. And then lambda would be given by what? It would be given by V over my frequency. Given that I have got my speed and my frequency, I would come and say 1,500 divided by 30,000. And then by that, I can be able to say 1,500 divided by what? By 30,000. This gives me 0.05 meters. That is what we expect to see on your calculations. And that becomes my lambda, which is my wavelength. Give two other uses of ultrasound in the field of medicine. We can use ultrasound for what? We can use ultrasound to determine the healthy status of a fetus in the womb. Of a fetus in the womb. In the mother's womb. I'm sure you have heard people say that I'm going to my baby scan, I'm going to my baby scan, or else we need to go for a scan. I'm sure you have heard pregnant mothers say that we need to go for a scan. That scan uses what we refer to as what? Ultrasound. That ultrasound would be used to actually get to scan through. It will determine the health status of the fetus in the womb. That is to say, it will check the blood flow of that fetus. It will also get to check, you can even get to use that ultrasound to check what? To check the gender. You can use it to actually monitor the fetus in the womb. So that is one of the what? That is one of the uses of ultrasound in medicine. This ultrasound can be used to what? It can be used to cure cancer. That is to actually burn the cancer. It can be used to cure cancer or else to burn the cancer. That is the method that is used in the cancer treatment. So you can say it is used for cancer treatment. And then it can just be used generally to what? To monitor or else to determine blood flow. It can be used to determine blood flow in the what? In the fetus of the womb, to know if the blood flow is moving in the rightful direction. I can just get to give you these two because they said two other uses of what? Ultrasound in what? In the field of medicine. Now let's go to question number what? Question number 5. Question number 5 is now saying, consider the electromagnetic spectrum below and answer the questions that follow. So the electromagnetic spectrum is given above, and then they're saying, use the table to answer the question that follows. Define the term a photon. What is a photon? So we know that a photon is a pack of energy, is a packet of energy. So it is a packet of energy or else a quantum. You can define a photon as a quantum of energy. Quantum just refers to a packet, a pack of energy. So you choose which definition do you want to use there. You can say it is a what? It is a pack of energy, or else it is a quantum. Give the names of the electromagnetic radiation A and B. So we start by radio waves, microwaves, infrared. We come to what? Visible light. So what is in between infrared and ultraviolet is what? Is what we call visible light. And then after ultraviolet light, we go to what? To X-rays, just before gamma rays. So A is what? Visible light. And B is what we call X-rays. And then 5.3, for radiation A with a frequency 2.5 times 10 to the power 16 hertz, calculate the energy of its photon. So here we need to calculate the energy of a photon that is having a frequency of what? Of 2.5 times 10 to the power 6 times 10 to the power 16 hertz. So here we are given the frequency. So we know that energy of a photon is given by H times F, where H is the Planck's constant and F is the frequency. So here we would come and say E is equal to H times F, and the Planck's constant is given in your information sheet. This Planck's constant is equal to 6.63 times 10 to the power negative 34. It is given in your information sheet. So what we need here is the frequency, and we are given the frequency, which is what? The frequency is 2.5 times 10 to the power 16. And our energy would be measured in what? In joules. So what becomes that? So we need to go and punch in our calculator. We get to say that 6.63 times 10, which is to the power of negative 34, multiplied by 2.5 times 10, which is to the power of 16. And the answer there becomes, the answer that I'm getting, it's 1.657 times 10 to the power negative 17. So that is the answer that I'm getting, 1.657 times 10 to the power negative 17 joules. Don't forget to write your what? Your units there. And your units are joules. That is how you calculate the energy of the photon that is having a frequency of what? 2.5 times 10 to the power 16. Now they're saying, explain why electromagnetic radiation B is best suitable for scan bones and not radiation A. And we said radiation A is visible light, radiation B is X-rays. So we are saying that radiation B, which is your what? Which is your X-rays, have a higher penetrating power. They've got a higher penetrating power that can scan through bones. What do we mean by scan through bones? It can actually give you what? White reflections, or else it can give you white light when you scan through bones. So that if you are having a fracture within a bone, you can actually get to see that fracture, which is a gap in between the scan that you'll be having. But however, now, if we now get to look at radiation A, which is visible light, it does not have enough penetration power. So radiation A, which is your visible light, does not, so this will give you a white image. That white image, you can actually get to see through it. So here we're saying radiation A, which is visible light, does not have enough penetrating power. Penetrating power to scan through soft tissues. To scan through soft tissues. So it does not have enough penetrating power to scan through soft tissues. So that is the difference. Our X-rays, they have what? Higher energy, which leads to higher penetrating power. Whilst visible light has got what? Lower energy than this, which is not enough energy. So it has got lower energy. This would translate to lower penetrating power. That is the explanation that we are supposed to give there. Now, that is the reason why B would be best suited to scan bones, not radiation A. Now, calculate the wavelength of radiation B if its photons have energy of that. Now, allow me to wrap this. If you want to write notes or else your answers for revision, you can pause and rewind back. Now, calculate the wavelength of radiation B if its photons have an energy of. We know that the energy of a photon is given by hf. And we know that we said V is equal to what? F lambda. Now, when we have radiation, this will take the speed of light, which is c, which is given by what? 3 times 10 to the power 8. Now, this would be written as c is equal to F lambda, so that our lambda can be given by c over what? So that our frequency can be represented in terms of what? Of F is equal to c over lambda. When I want to make this the subject, I'll just take this one, that other side, I'll divide there. So it will be c over lambda. So when I'm having frequency, I'll substitute by that. Wheresoever that I have frequency, I'll substitute by that. So I say that V is equals to F lambda, and we are saying that for light or else for radiation, we are using the speed of light. That would be C is equals to F lambda. So I can now represent my frequency in terms of what? The speed of light over the frequency, over the wavelength. Now I'll substitute this into my equation of energy. That would be H bracket C over lambda. So that would be E is equals to what? E is equals to HC over lambda. Now I'm given the energy of that radiation. Now, since I'm given the energy of that radiation, what I'm just going to do, allow me to wrap this. We used it before. The energy of my radiation, I'm going to substitute it here, so that I would have what? I would have 7.25 times 10 to the power negative 13 joules being equal to what is my H. This constant is always given in your information sheet. You just get to go and find H represent Planck's constant. Planck's constant. So you just have to go and take that value, which is 6.63 times 10 to the power minus 34. You substitute it here, and then the speed of light, we know that the speed of light is 3 times 10 to the power 8. That is the speed of light. I have already mentioned that C, the speed of light is 3 times 10 to the power 8. That is what you take there. So now what I'm left with is this lambda. That is what I'm looking for. That is what I'm going to make the subject there. So I'll interchange these two. So I'll take this one that other side, and then I'll take this one that side. So I'll be left with what? I'll be left with my lambda, which is my wavelength, being equal to 6.63 times 10 to the power negative 34 times 3 times 10 to the power 8. So this is the speed of light. This is Planck constant divided by my energy, 7.25 times 10 to the power negative 13. And what becomes my wavelength? So I'll just go to my calculator. 6.63 times 10 to the power negative 34 times 3 times 10 to the power 8 divided by 7.25 times 10 to the power negative 13. That becomes my wavelength would be the same as 2.74 times 10 to the power negative 13 times 10 to the power negative 13 meters. That becomes my wavelength. So what is more important is knowing how you get here. That is from this equation. That is what is more important there. Now, let's look on question number 6. Question number 6 is saying two identical metal spheres A and B on an insulated surface carry charges negative 5.3 times 10 to the power negative 6 coulombs and positive 4.7 times 10 to the power negative 6 coulombs respectively. The spheres are brought into contact with each other. State the principle of charge quantization. So I brought you the definition of this. I brought you the definition of that so that we get to know that definition. It's not usually given in some textbooks, but in some you would find it. So that is the principle of quantization. It says that every charge in the universe consists of an integer multiple of the charge of one electron. So every charge in the coulomb, which is 1 coulomb, is given by the number of the coulombs that you have times, just pardon me there, so 1 times the what? The charge of 1 electron. The charge of 1 electron. So you would actually get to say 1 charge or of every charge that will be given there consists of an integer multiple of the charge of 1 electron. You would see where it applies. Let's go back to our question. You would see where it applies. Now, calculate the number of excess electrons in sphere B. So you would see that this is sphere A and this is sphere B. So in representation, I would have said that I have sphere A and I have sphere B, and sphere A having a charge of negative 5.3 times 10 to the power negative 6 coulombs. This one having a charge of positive 4.7 times 10 to the power negative 6 coulombs. So you would see that sphere A is the one that is having extra electrons. So here they made a mistake by saying B, how much is it having in excess of electrons? But however, since we are already given this question, we just need to determine the number of electrons that would be given what? That would be given by that charge. So what we do is, you know that the number of electrons is given by the what? by the charge divided by the what? By the charge of each electron. So let me just get to bring you some formula sheet so that at least you get to see where I'm taking these formulations. At least you get to see where I'm taking those formulations. So here we are. The number of electrons is given by that formula, where we are saying N is the number of electrons and the charge that you are given all over the electron charge. And the charge of each electron is equal to what? 1.6 times 10 to the power 19. So this is just what I'm going to use there. This is what I'm just going to use from our question that we are given. So that is what I'm just going to what? To use there. So here they're saying calculate the number of excess what? Electrons. So I'm just going to use, pardon me, this is just giving me a hard time now. So the number of electrons would be equal to, what is charge of B? It is 4.7 times 10 to the power negative 6 divided, what is the charge of an electron? 1.6 times 10 to the power negative 19. Now I will just use the magnitude of that so that I get the number, because I'm just looking for the number. So I would say 4.7 times 10 to the power negative 6, which is equal to that divided by 1.6 times 10 to the power negative 19. That gives you the number of the number of electrons there. The number of electrons that I'm getting here, they are too much. So I've got 2.9 times 10 to the power 30 electrons. That is the number that I'm getting if I divide this by that. So let me just repeat it. Maybe I made a mistake. Let's confirm that 4.7 times 10 to the power of what? Negative 6. If I divide by 1.6 times 10 to the power negative 19, it is giving me the same. So that becomes the number of electrons. So that becomes the number of electrons, which is what? 2.9 times 10 to the power 30. But however, though, because of this confusion of excess electrons, if you had came and used this one divided by the number of electrons, I'm sure they would have marked you correctly. But let's just get to take note to say that number of electrons is given by the charge that you are given, which is of B, divided by the charge of each electron. That is how you calculate the number of what? Of excess electrons. Give a reason why we place charged spheres on insulated stands. We want to preserve or to conserve our charge. We place them on insulated spheres because insulated spheres, they do not transfer charges. So we want to conserve or preserve our charge. We want to, you can say that, to prevent loss of electrons, or you can say to conserve our charge. So an insulated stand will not transfer any charge. It will not transfer any electrons. So we want to prevent the loss of electrons. We are preventing the loss of what? Of electrons. That's why we use insulated stands. Will the electrons be transferred from A to B or from B to A? So electrons would be transferred from a negative to a positive. So the negative is the one that is having excess electrons. So we are going to transfer from what? From A to B. It is from A to B because A is having excess electrons. So A is the one that is having excess electrons because of this negative charge. That is the reason why I said when they say calculate the number of excess electrons, they were supposed to say excess of electrons of A, not B, because B does not have excess electrons. So I'm sure they made a mistake there. But however, you end up working with what you are given. Now, calculate the new charge on sphere A after it has moved away from each other. So, what happens is we are having sphere A and sphere B. Sphere A and sphere B. They will be brought to each other. That is, they have got negative and a positive. When they come to each other, we are going to have a total charge, which is charge of A plus charge of B. And then when they are separated, we are going to have individual charge after separation, which is charge of A plus charge of B divided by 2. That is what they want here. So allow me to create enough space that we are actually going to what? To use in determining our calculations. So let me use this side. And let's take the what? The charges. I have got charge of A, Q of A is equal to negative, or else let me just write it in terms of what? Of spheres there. Now I've taken my, I'm now trying to bring, sorry, I'm now trying to bring what I've just put there. Okay, fine. It will be fine. Okay, so I mistakenly hid my arrows, but however, it will be fine. Let's continue. We are saying that we have got charge A and we have got charge B. So charge A has got a value of what? Charge of A, it has got a magnitude of negative 5.3 times 10 to the power negative 6. This one has got a positive 4.7. It is 4.7 and what? 4.7 times 10 to the power negative 6. So these are the two spheres. These are the two spheres. Here I've got times 10 power negative 6 coulombs. Now, when they are brought together, the total charge becomes charge A plus charge B. When they are now separated, after separation, each individual sphere will carry an equal charge. So what is going to happen is now after separation, Q of each would be equal to Q total over 2. Now, what is Q total? That is what we want to calculate, and then we divide by 2. Then we would be able to determine our what? Our charge of each. So we are going to say negative 5.3 times 10 power negative 6 plus positive 4.7 times 10 power negative 6 divided by 2. That is the final charge after separation. So after separation, I'm just going to have negative 5.3 plus positive 4.7, positive 4.7. That gives me what? A negative. So I would have a negative 0. What? A negative. We are going to have a negative 0.6. A negative 0.6 there. A negative 0.6 times 10 to the power negative 6 coulombs. That becomes the charge of each after separation. And that is how you calculate that charge of each after separation. So let's actually get to see what the question was saying. The question was saying, calculate the new charge on each sphere after it has moved away from each other. That is how you calculate it. And then they're saying, calculate the number of electrons transferred from one sphere to the other during contact. Now, what you need to do is, for you to calculate the number of electrons, you need to calculate the change in charge. So change in charge is just final charge minus initial charge of each. And then for you to calculate the number of electrons, you now get to say the number of electrons would be equal to the what? To the change in charge divided by the charge of an electron. So what is the change in charge there? You would see that the change in charge becomes the final charge. We said the charge that we have now found, finally it is negative 0.6 times 10 to the power negative 6. That is the one that we are going to use being our final in either of the two. So you would come and say negative 0.6 times 10 to the power negative 6. I can say minus the initial, let me take off the positive, which is positive 4.7 times 10 to the power what? Negative 6, which will give you what? If I do that, my answer is supposed to be what? Let's use our calculators. So I now have negative 0.6 plus 4.7. That gives me 4.1. That gives me 4.1 times 10 power minus 6. Even if you had said that, even if you had taken negative 0.6 times 10 power negative 6 minus bracket minus 5.3 times 10 power negative 6, you are going to get the same answer, because here you'll be having a positive. So 5.3 minus 0.6 will give you what? 4.1. That is what you are going to get there. That is simply what you are going to get there. So if I actually get to say 5.3 minus 0.6, I'm going to get what? So here, something is wrong with our answer somewhere. I'm sure here where we what? I'm sure this answer, let me hold it there. I want to correct something. If we do negative 5.3 and then we add 4.7, what becomes our answer? 5.3 plus 5.3, negative 5.3 plus positive 4.7. We are getting 0.6. 0.6 divided by 2. Yes, we were supposed to divide by 2 there. So this answer that I've wrote here is straight from the above. They were just supposed to say what? Divided by 2. Just pardon me there. You can correct me. That's why I usually like people to use their what? Their calculator, so that the answer that you get here, it's negative 0.3 times 10 to the power minus 6. So once we have this now, I can now come and say this is the new charge for each. If that is the new charge for each, where I'm putting my new charge of each, that is what I'm going to put. So that here I'll say what? 0. What? Negative 0.3 times 10 power negative 6. Then negative 0.3 times 10 power negative 6, negative 4.7, it will give you what? It will give you a negative 5.0. It will give you a negative 5.0 times 10 power negative 6. And then if you come here, you also put negative 0.3 there. You would have negative 0.3 times 10 to the power negative 6. And then if you say positive 5.3 minus 0.3, you would get 5.0, which is just the same. And then to get the number of electrons now, this is the change in charge. To get the number of electrons, you now say change in charge over the charge of an electron, which is just negative 5.0 times 10 to the power negative 6. all over negative 1.6 times 10 to the power negative 19. And then that should give you the what? The number of electrons, which is the number of electrons transferred from one sphere to another. That would become 5 times 10 to the power negative 6. I divide there by 1.6 times 10 to the power negative 19. I would actually get what? 3. I would get 3.15 times 10 to the power 13 electrons. So those are the number of electrons transferred from each sphere. Now let's go to our next question, which is question number 7, which marks the last question of our question paper. So question number 7 is now saying, consider the following circuit below. The reading on voltmeter V1 is 6 volts. The ammeter reading is 1.5 volts. So the reading on this voltmeter is the one that is what? 6 volts. And now we do not know the reading there. Now it is said, define the potential difference. We know that potential difference is simply what? This is the work done per unit electric charge. Work done per unit electric charge, where you would represent it by saying volt is equals to work done per unit charge. This is the work done per unit electric charge. Calculate the magnitude of the reading V2 if 8,000 joules of energy is used by 735 coulombs. So now, we assume that this 8,000 joules is being used for this circuit. So the voltage here, which is the total voltage, your total voltage would be equal to the what? To the work done per unit what? Coulomb of charge. That's why they said determine the potential difference. So defining the potential difference, we know that it is the voltage across what? Our conductor. So this was going to be equal to what? 8,000 joules per unit 735 coulombs. And what becomes the answer? You say 8,000 divided by 735. That gives you an answer of what? 10.884 volts. But however, is it what is asked? We are asked V2. So we know that the voltage in series is summative. We know that total voltage in series, so you see Vt is equals to V1 plus V2. So when I want to find V2, I will just get to transpose this to the other side so that it becomes Vt minus V1. So that becomes 10.884. That becomes the voltage there would be 10.884 minus 6 volts. That's why they give you this. That's why they gave you that 6 volts. So if I do 10.88 minus 6, I would get what? I would get 4.884 volts. That is the reading that you are going to find on what? On voltmeter V2. So that was that for our question paper, which was written as a controlled test in March 2025 from the OR Tambo Inland District. So guys, let's meet in our next coming videos as we continue to do our revision and practice as we prepare for our March test. Thank you so much.